Hi Chris, Dave from Basic Micro UK. I've been looking at this little project that you're doing, and I've made some changes to the program that you sent me, and basically I've added a new variable onto this program called P2 delay. It's a byte variable, range 0 to 255. The next thing that I've made a change to is just a note here on the setting up of int EDG. That currently was 0, which means basically start the time delay from the trailing edge of the pulse that comes in on P0. If you set that to number 1, that will actually start the delay from the rising edge of the pulse that comes in on P0. Now with the current setup, whichever way you set this interrupt to trigger, the latency between the pulse triggering on P0 to P2 going high is 2.99 microseconds, and that is basically fixed. Okay, so the next thing that I've done is in the section that you call your routine to actually measure PW, you divide it by 1000 to give a range of 0 to 1000. On this system you've only got really 0 to 255, and I'll go into that a bit later as why you can't have a pulse longer than that, but the P2 delay is set here, and it's just been set directly to 10s SW. The actual test results from this, I've actually put down what the values you actually get are, so it's a bit of a compromise on the exact values, but they are consistent. If you set P2 delay to a 2, you'll get 2.19 microseconds pulse. If you set it to a 5, it's 5.19, and so on. 75 will give you exactly 75 microseconds, and 250 will give you 249.5 microseconds. Now in the main routine, all I do is actually send out to the serial port the value of P2 delay, and then the interrupt service routine itself, when you come into there, it sets the port P2 high. Then it goes into this delay routine. This basically copies P2 delay into the working register, runs around this loop the amount of times required to give you the delay, basically 5 cycles when the chip is running at 20 megahertz is equivalent to 1 microsecond. So it loops around here enough to give you the 1 microsecond delay, and then it sets the port low again. Now when this program runs, effectively this interrupt will just be self-contained and the main loop will be going round. There will be a point, because you're delaying in the interrupt, where the interrupt's actually holding up the main program, and at the moment there's not a lot going on in there, but where it will cause a problem is with the serial out routine, because this serial out actually relies on software delays. It's a software serial port, not a hardware driven UART. So when we get to a higher frequency on the input, you'll notice that this actually will start to corrupt. At the moment I've got some test software set up, and it's downloaded into this board that you can see here. So all I've got here basically is the same IC that you're using, a Nano 28X, and the way it's set up is an interrupt is being generated on P0 actually from one of the other ports. In the main loop I've just set a pulse out command to generate the interrupt, and then that interrupt, as well as the result that's coming out on P2, is being sent to the logic analyzer. And if I move those wires out of the way, you may just see that, but it's actually giving you a pulse now. Let me just zoom in and see if you could actually see that. So you can see it's a bit out of focus, but you can see the interrupt coming in on P0, and then it's giving a pulse out on P2. On the actual software itself, I've got that set so that it shows the delay that's been set up on a potentiometer, and here you can see what P2 delay is, and that's set by a 10-turn potentiometer. Now I've also got a logic analyzer selected, so if I go into the logic analyzer and have a look what that's telling us at the moment, this is a very basic tripod, so it's probably not coming out perfectly, but here you can see the 2 pulses. The top trace is the pulse going in on P0, and the bottom trace is the output on P2. So at the moment the top one, it's only coming in at 3 Hz because it's just done in the main program, and the pulse width is 9.38 microseconds, and because int edge is set to 0, it's starting the timer pulse or the interrupt on the trailing edge. So in here I can actually put on some markers. If I put a marker on the trailing edge of the interrupt on P0 and then also put a marker on the start of the interrupt, the distance between those two markers is 2.98 microseconds. You can see that on the screen there. And we can also then look at the pulse width, and we can see that that's 10.18 microseconds, and the value that's coming in from the potentiometer at the moment is 10 microseconds, or 10 on P2 delay, if you can see that on the bottom. So if I put P2 delay up by raising the potentiometer, I can raise that to 50. So that's P2 delay is now set to 50. There we go, just nudge the potentiometer there. So that's 50, and then on the logic analyzer I can reset that. So I'll do another capture. Here's the new pulse width, and you can now see that that pulse width is, if you can resolve that, we're now at 50.7 microseconds. So this is effectively working synchronously at the moment, because what I'm doing is in the main program loop I'm actually generating a pulse on a pin that's then coming through into P0. So now what I'm going to do is, rather than running synchronously from the program, I have here a frequency generator. So I'm going to hook up this frequency generator to provide the pulses, and then just changing the hardware at the other end, so that now rather than using the pin out on the microcontroller, we're actually using the pulse from the generator, and currently this is set to give a 1 Hz signal. So back on the hardware again, you can see now P0 is pulsing 20% duty cycle and 1 Hz. So if we go back to the logic analyzer and I do a refresh on that, that's just calculated, we can now see that the pulse is coming in at the top, which there are 1 Hz, and the pulse width coming out at the bottom is 50.6 microseconds, because that's what the rate the potentiometer set up at the moment. That's still coming in as 50. Now if I actually increase the rate now, that's coming in currently at 1 Hz. I can actually come in at 10 Hz, and now you can see the much more frequent pulses on the logic analyzer side of things. If I do a refresh on that, you can now see that we've got much more frequent pulses on the top, and the pulses following that again, if I zoom in, are 50.06 microseconds. Now on the logic analyzer we'll be able to see what happens with the pulses. So I'm going to increase now to 100 Hz, and now on the actual hardware it's almost a solid LED that we've got on P0, but you can see that it's a lot dimmer on P2. And an interesting thing to note now is that at 100 Hz, if you look at the serial communications, it's now started to be corrupted. You're just getting the odd character that's coming out incorrect there, and that's because the interrupt plus the delay that's occurring in there is starting to interfere with the serial communication, so it's actually getting framing errors. And on the logic analyzer, if I go into that and refresh again, you can now see that we're running at 100 Hz at the top, and we've got exactly 50.06 microseconds on the output again. So on the frequency generator, what I'm going to do now is just actually increase from 100 Hz and go up to 1000 Hz. And if you have a look at the communication, we're now at 1 kilohertz, and you can see the serial communication now has become almost unusable. If we look at the logic analyzer again, I'll do a refresh on that, so you can see we're at the old 100 Hz at the moment. Refresh, and now we're at 1 kilohertz, and the pulse width is still exactly 50.06, so the pulse is working. You've still got exactly the same latency of 2.98 microseconds between the end of that pulse and the start of the next one, but you're having problems now with the communications. What I'm going to do now is increase the frequency, So I'm going up. Now we're starting to get all sorts of different error coming up now. We've got in beep characters and things like that coming on the terminal. That's what you're hearing there. We're now at 9.5 kilohertz. Now I know your maximum frequency is going to be 10, but if I reset the logic analyzer, alright, okay, we can see we've got 9.53 kilohertz coming in at the top, and we then still have that delay, and we have our pulse again coming out at still exactly 50.07 microseconds. They're going to remember, we're only running at 50 at the moment. Now if I increase this pulse by turning the dial up, as I go up, you'll see that the pulse width, if I refresh the logic analyzer again, is actually getting longer, and we're close now. We're now at a 75 microsecond pulse. Now we're at 79, going up a bit higher. Now we're at 88. Okay, now we're at 97 now, and you can already see that the pulse is almost longer than the incoming interrupt. So as I go a bit higher, we're now at 97.3. Now we've reached a point where we can't get to, or we're going to get a problem, because the interrupts are now actually going to be halted. So what's happened here is we've set the pulse to 142.8, so basically it's 142 coming in on the P2 delay parameter, but because we're coming in at 9.5 kilohertz, effectively what's happened is we've had an interrupt, and we've missed an interrupt on P0, and that's why I said that you know, it wouldn't be practical to have a 10 millisecond pulse at all, because if your incoming frequency is 10 kilohertz, it's going to be way longer than the frequency that you're actually applying. So 0 to 100 or 0 to less than 100 is going to be the maximum you can do. If I wind the potentiometer back down again to a much lower value, then reset, you can see now that it is practical to have a higher frequency coming in. Anyway, that's something that you can experiment with. I don't know how long it will take for this to download into YouTube, so you can have a look at it, and I'm not sure if that will happen tonight, but I can send you the software that we've got so far, and it's something that you can experiment with. But you've got to look at these things, think about that serial communication, because that's going to be a problem. You may have to change to a hardware UART. I'm sure you're only using that for diagnostics, and possibly you won't need it in the final version, but it just gives you an idea, and it shows you actually what's happening in the software here. I hope that helps.